this presentation we're going to look at the negative binomial distribution, and what we're going to do is actually see how the negative binomial distribution can be used to characterize Poisson distributions where the mixing distribution of the Poisson rate is a gamma distribution. So essentially this is what they call a Poisson-Gamma mixture, and a Poisson-Gamma mixture is a negative binomial distribution. Now this comes up quite a lot in insurance applications and so on, so it's the type of thing that actuarial students might study. So we can view the negative binomial distribution as a Poisson distribution with parameter lambda, where lambda is itself a random variable distributed as a gamma distribution with shape parameter r and scale parameter theta equals p divided by 1 minus p, or correspondingly theta equals 1 minus p divided by p. We'll just come back to that shortly. Okay, I'll just go over it again down here just to actually sort of see how it fits. So this is the actual question. Suppose the number of claims in a year for an insured has a Poisson distribution with mean capital lambda. That's capital lambda. The random variable lambda follows a gamma distribution with a shape parameter alpha equals 2.5 and a scale parameter theta equals 1.2. 1,000 insured are randomly selected and are to be observed for 1 year. Determine the number of selected insured expected to have exactly 3 claims at the end of the 1 year period. Okay, so this is where we use the negative binomial distribution. Now usually we would sort of denominate the negative binomial distribution in terms of r and p. Okay, those are the parameter names. Sorry, that's not p, that's p. Okay, in this case r takes the value of alpha from the gamma distribution, and p takes the value of 1 divided by 1 plus theta from the gamma distribution, where theta comes to the gamma distribution. So that's the setup there. It's just we have the values of p set up accordingly from the theta from the gamma distribution, and we set it up accordingly. Just a sort of important remark, now something to watch out for is that the varying structures of the negative binomial distribution come into play there quite a lot. But anyway, we'll sort of bypass that for the time being. Just watch out for that in other sort of presentations. We'll just sort of keep going as we are. So with this being a Poisson-Gamma mixture, the number of claims in a year from a randomly selected insured has a negative binomial distribution. The probability mass function is given as follows: k plus 1.5. From k plus 1.5, choose k. There we have it there. 1 divided by 2.2, that is 1 plus 1 plus 1.2 to the power of alpha. There we go, which is 2.5. And likewise, there we have 1.2 divided by 2.2 to the power of k. Now, this one here is interesting. We'll just sort of come to that shortly. But let's just say, for argument's sake, k is equal to 1. Okay, how would we go about that? That would be 2.5, choose 1, and that's going to be 2.5. Now, how did I know that? Let's do k equal to 2. So that's going to be, let's look at the factorial first. That's 3.5. Sorry, let's set it up first actually. So that is, let's just actually look at the denominator of how we'd work that out. We sort of start with the denominator, go 2 by 1, evaluate 2 factorial. And then what we do is we start off with 3.5 and decrease by 1 each time until the numerator corresponds to essentially equal amount of terms in the numerator as the denominator. So when the denominator hits 1, the numerator hits 1. That's sort of general idea. That's if you're used to working with binomial coefficients, you hopefully are used to that by now. But we work it out the same way essentially. So you can have 2.5 in there. Anyway, what the question asks us is the probability of x equal to 3. So that is from 4.5, choose 3, find the binomial coefficient of that. That's just calculator work there. We know that looking for x equal to 3, so 1.2 divided by 2.2 to the power of 3. Calculator work and calculator work. This is the interesting part here. From 4.5, choose 3. The binomial coefficient of 4.5 and 3. So that the numerator, or sorry, look at the denominator. That's 3 by 2 by 1, 3 factorial. And we work out the numerator as follows. So the first term there is 4.5, then 1 minus that, 3.5, then 1 minus that, 2.5. And again, there's a match up there, numerator, denominator, until the denominator hits 1, the sort of countdown approach. Now, so working that out, we should get 6.5625. Basically, this is calculator work now. So 0.14835, which out of 1,000 people is 148.35, so nearly 149. We would expect 149 out of 1,000 to have 3 claims in a year. Okay, so that's it. Straightforward enough. This is the sort of tricky bit there, getting the hang of those. They're not that tricky at all, but just people are not used to them. Alright.